Hello all, I am Sailaja, working as Assistant Professor in the Department of Physics of Mlritm. Today, I am going to discuss about quantum physics and solids. Under quantum physics and solids, the topics which I am going to explain are Introduction to Quantum Mechanics, Black Body, Radiation. So first let us see Introduction to Quantum Physics or Quantum Mechanics. Before going to study what is quantum mechanics, first let us understand what is classical mechanics, its failures and how quantum mechanics has developed. So first, classical mechanics. Classical mechanics means it is a branch of physics which explains the motion of microscopic objects. Microscopic objects means the objects which are larger in size. It was introduced by Newton in the year 1684. Classical mechanics is based on Newton's laws of motion. Classical mechanics is based on Newton's laws of motion. Therefore, it is also known as Newtonian mechanics. Now, according to classical mechanics, we can find exactly the position, velocity, acceleration, etc. of a system at any instant. And by using equation of motion, these quantities can also be known at a later instance also. Now, by using classical mechanics, the motion of objects like sun, planets can also be known. So, thus we can say that classical mechanics gives correct explanation for the behavior of macroscopic objects. And according to classical mechanics, oscillating electrons will radiate energy continuously. So, next let us see the drawbacks of classical mechanics. Classical mechanics could not explain, first one, the motion of atoms, electrons, protons, etc. So, when classical concepts or when classical physics is applied to particles of atomic dimensions, when classical concepts are applied to particles of atomic dimensions means the particles which are very smaller in size, for example, in the range of angstroms and nanometers. So, to such type of particles, when classical concepts are applied, it failed to explain their behavior. So, from this we can say that classical mechanics cannot explain the motion of microscopic particles like electrons, protons, neutrons, etc. And the next failure is the stability of atoms. We know that an atom consists of nucleus at the center. Around which electrons are revolving in circular orbits. So, according to classical mechanics, this negatively charged electrons experiences attractive electrostatic force due to the positively charged nucleus. So, due to attractional force, what happened? They should come closer to each other. Now, secondly, the electrons experiences centripetal acceleration. Here, the electron experiences centripetal acceleration. Then, we know that an accelerated charged particle will radiate energy continuously. So, therefore, we can say that here the energy of the electron will decrease continuously and it should come closer and closer until it collapses with the nucleus. Since the energy of the electron is decreasing, because of this what happens? The electrons will come closer and closer to nucleus until it is colliding with the nucleus. So, this shows instability of the atom. So, this statement is contradictory to the observed fact of stability of atom. So, from this we can say that classical mechanics could not explain the stability of atoms. Next, third one is origin of discrete spectra of atoms. So, when the spectrum of atom is observed experimentally, they found that the spectrum is consisting of discrete set of lines. Instead of single line, they observed discrete set of lines. That is, splitting of the single line into many lines. Why the single line is splitting into many lines was not explained by classical mechanics. Therefore, we can say classical mechanics could not explain the origin of discrete spectra of atoms. Next drawback is it could not explain variation of specific heat of metals and gases. Next, classical mechanics was unable to explain the phenomenon like photoelectric effect, Compton effect, Zeeman effect, Raman effect, etc. The last drawback which is important is here the spectrum of blackbody radiation. The spectrum of blackbody radiation. Our next topic is blackbody radiation. There we'll study what is blackbody, its spectrum in detail. Here we'll simply see how classical mechanics has failed to explain the spectrum of blackbody radiation. So the radiations emitted by a blackbody consists of all wavelengths. It consists of all wavelengths. The radiation emitted by the blackbody consists of all wavelengths. Okay. So scientists, they made attempts to explain how energy is distributed among all these wavelengths. How energy is distributed among these wavelengths at different temperatures. The blackbody emission consists of all wavelengths. So attempts have been made by the scientists to know how energy is distributed among all these wavelengths at different temperatures. So first, Stephen is a scientist. He has given Stephen's fourth power law. Stephen has given a law known as Stephen's fourth power law, that is E is proportional to T power 4. So this law states that here the total energy of the blackbody radiator per unit area per second is proportional to fourth power of temperature, fourth power of absolute temperature. That means here this Stephen's law is giving you the total energy of the radiator, but here it does not throw any light on the distribution of energy among different wavelengths at different temperatures. So later the distribution of energy among different wavelengths at different temperatures was studied experimentally by Lummer and Springstream. Lummer and Springstream, they have studied the variation of energy among different wavelengths and at different temperatures, and they have performed an experiment and they have plotted a graph between wavelength and energy, and they got curves like this at different temperatures. This is at T1, T2, at T3. These are the experimental curves drawn by Lummer and Springstream. Later, scientists has now made attempts to explain these experimental curves theoretically. So first, Wien is a scientist. He has given Wien's law. Wien's law. So Wien's law. So Wien's said that the maximum energy point shifts towards shorter wavelengths as temperature is increased. That is, we can write lambda m is inversely proportional to 1 by T, or lambda m into T is equal to constant. This is Wien's law. So first, Wien's has given Wien's law in order to explain the experimental cause of blackbody radiation theoretically. But this law is valid for shorter wavelengths. This law is valid for shorter wavelengths and it could not explain the longer wavelengths. So this law is applicable only for shorter wavelengths. It is unable to explain the longer wavelengths. Next, to overcome this problem, Rayleigh-Jean has given Rayleigh-Jean's law. So Rayleigh-Jean's law, he has given an expression for energy distribution. Its value is E lambda d lambda is equal to 8 pi kt by lambda power 4 d lambda. So this is Rayleigh-Jean's law, and this law is applicable for longer wavelengths. This law is applicable for longer wavelengths. It was unable to explain the shorter wavelengths. So longer wavelengths was explained by Rayleigh-Jean's law. Shorter wavelengths were explained by Wien's law. So these both laws are unable to explain the experimental curves throughout the whole range of wavelengths. Why? Because these laws are explained on the basis of classical mechanics. These laws are explained or derived, these laws are derived on the basis of classical mechanics. So later Paschen is a scientist. He suggested that the basic assumptions of classical mechanics are wrong. The basic assumptions of classical mechanics are wrong. So therefore now, in order to explain these experimental curves, Max Planck in the year 1900, he suggested that we would get the correct results if we take the energy as discrete instead of taking energy as continuous energy. If you take discrete energy, then we will get the correct results. So basing on this, he has made some assumptions and he has derived an expression for it, and that is known as Planck's radiation law. So what is Planck's radiation law? Planck's radiation law is E lambda d lambda is equal to 8 pi hc by lambda power 5 into 1 by e to the power of hc by lambda kt minus 1 d lambda. So this is known as Planck's radiation law. And this formula agrees well with the experimental curves over the whole wavelength range. This formula is agreed with the whole wavelength range. So this formula is applicable for the experimental curves over the whole wavelength range. So in this way, quantum theory has evolved. So next we will see what is quantum mechanics. So quantum mechanics means it is a branch of physics which explains the motion of microscopic particles like electrons, protons, neutrons, etc. And why quantum mechanics has developed in order to explain the shape of blackbody radiation curves. Max Planck in 1900 proposed the quantum theory. This was developed by Einstein, and Einstein explained quantum theory to explain photoelectric effect. Next we will see what are the assumptions made by Planck. First assumption is he said that a blackbody radiator consists of simple harmonic oscillators of all possible frequencies, and these oscillators cannot emit or absorb energy continuously, but they emit energy only when the oscillator jumps from one energy level to another energy level. Oscillators emit or absorb energy in discrete amounts, that is, energy of oscillators is quantized. So just now we have seen only when the energy of the electron is considered as discrete, then only we are able to explain the experimental curves of blackbody radiation over the whole range of wavelengths. So discrete amounts, energy is discrete amounts means energy is not continuous. That means only energy can have certain amount of values. For example, we know energy of the photon is how much? E is equal to nh nu. If n is equal to 1, then E will be equal to h nu. If n is equal to 2, E is equal to 2h nu. If n is equal to 3, E is equal to 3h nu. That means when n is equal to 1, there will be one electron. At n is equal to 2, we have one more electron. At n is equal to 3, we have one more electron. That means between n is equal to 1 and n is equal to 2, there will not be any electrons. You can see here. So this is quantized energy, this is continuous energy. So according to quantum mechanics, energy is quantized. According to classical mechanics, energy is continuous. Energy is continuous energy means the electron can have any value. Whereas quantized energy means here the energy it can have only particular value of energy. For example, here you can say n is equal to 1 means h nu. So this is your h1. Here you have one electron. N is equal to 2, h2. One more electron is present here. For n is equal to 3, h3. One more electron will be present here. Okay, so in between h1 and h2, we will not find any electron. So E is equal to nh nu. What is n here? It is a quantum number. Nu is frequency of oscillation. H is your Planck's constant. What is the value of Planck's constant here? 6.625 into 10 to the power of minus 34 joule second. So on the basis of above assumptions, Planck derived a formula for energy distribution of black body, that is E lambda d lambda is equal to 8 pi hc by lambda power 5 1 by e to the power of hc by lambda kt minus 1 d lambda. So this formula agrees well with experimental curves throughout the whole range of wavelengths. So next we'll see black body radiation. So before going to black body radiation, let's first let us understand what happens when light is incident on any object. So when light is incident on any object, three phenomenon takes place. What are they? Reflection, transmission and absorption. So here the phenomenon of reflection is responsible for the color of the object. The phenomenon of reflection is responsible for the color of the object. For example, you can see when radiation or light is incident on white surface, we know that light consists of all colors in it. So when light is incident on white surface, all colors are reflected. So since all colors are reflected here, the surface appears white in color. Similarly, when light is falling on a black surface, the black surface is absorbing all the colors. It is not reflecting any color. Therefore, the surface appears black in color. Now, when light is falling on a red color surface, all colors are observed except the red color light. Red color light is reflected. And all other colors are observed by the surface. So, since here we have seen the phenomenon of reflection is responsible for its color, since here red color light is reflected, the surface appears red in color. So now let us define what is thermal radiation. Thermal radiation. So thermal radiation means it is the energy possessed by the radiation possessed by a body due to its temperature. Thermal radiation. The radiation emitted by a body by virtue of its temperature is known as thermal radiation. This thermal radiation, it is an inherent property of all bodies. That means all bodies will emit or absorb radiation continuously. Thermal radiation means the radiation emitted by a body by virtue of its temperature or due to its temperature. Due to its temperature, the radiation emitted by a body is known as thermal radiation. This thermal radiation is inherent property of all objects. That means all objects will radiate temperature. So Prevost theory of heat exchange. Prevost is a scientist. He has given one theory known as Prevost theory of heat exchange. Prevost theory of heat exchange. So this theory stated that all bodies will emit as well as absorb radiation continuously as long as its temperature is above 0 Kelvin. As long as its temperature is above 0 Kelvin. Okay. So thermal radiation means the radiation emitted by a body by virtue of its temperature is known as thermal radiation. Thermal radiation is an inherent property of all bodies, and according to Prevost theory of heat exchange, this theory is saying that all bodies will emit or absorb radiation continuously as long as its temperature is above 0 Kelvin. Okay, here if the temperature of the body is larger, it will emit shorter wavelengths. If the temperature of the body is low, then it emits longer wavelengths. For example, human body also emits radiations and absorbs radiations, but we cannot see the radiations emitted by the human body because they are very smaller in value. Next, we will define what is black body. Now, a black body is a body which absorbs radiation of all wavelengths incident on it. Radiation consists of all colors in it. So, whenever this radiation is falling on a black body, what is happening? It is absorbing all the colors. It is not reflecting any color. Therefore, it appears black in color. You can see a black body is a body which absorbs radiation of all wavelengths incident on it. It is absorbing all the radiations. It is not emitting any radiation, or it is not reflecting any radiation. Therefore, it neither reflects nor transmits any of the incident radiation. So, therefore, it appears black in color, whatever may be the color of the incident radiation. Now, we will define what is the black body radiation. The radiation emitted by a black body when it is heated is known as black body radiation. The radiation emitted by a body when it is heated is known as black body radiation. So whenever radiation is falling in a black body, it is absorbing all the radiations. So similarly, whenever you are heating it by giving some temperature, it will emit all the radiations. It will emit all the radiations. It is absorbing all the radiations and it will emit all the radiations. So the radiations emitted by a black body is known as black body radiation. For example, you take an iron rod and you heat it. When you are heating it at one particular temperature, the iron rod will turn into it, or it will emit a dull red color. If you still increase the temperature, it will emit dark red color. If you still increase the temperature, it will emit white light. If you still increase the temperature of the rod, it will emit blue light. Okay, so from here we can see that as the temperature is increasing, it is emitting light of shorter wavelength. Just now we have seen, if the temperature of the body is high, it will emit shorter wavelengths. If the temperature of the body is low, it will emit longer wavelengths. So we can see here the wavelength of red light is very large when compared to the wavelength of blue. So as the temperature is increasing, it is emitting light of shorter wavelengths. Now in the universe, there is no perfect black body. So no actual body is a perfect black body. Now lamp black or platinum black in nature, lamp black or platinum black may be regarded as black body. Why? Because they absorb 99% of incident radiation. Since they are absorbing 99% of incident radiation, lamp black and platinum black are considered as black bodies. Now Kirchhoff's law. Kirchhoff's law is saying that Kirchhoff's law is saying that whenever, if a body is able to absorb the radiation, then it should be able to emit the radiations also. It will be able to emit the radiation also. So basing on this law, since black body is absorbing all the radiations, so what it is saying, if it is absorbing the radiations, it should be able to emit the radiations also. Since here black body is absorbing all the radiations, it will emit all radiations also. So from this, what we can say, that means a black body is a good absorber as well as a good radiator. Next, here two scientists, Ferri and Wiens, they have constructed two black bodies. Ferri's black body, Wiens' black body. So now let us see the construction of Ferri's black body. This Ferri's black body consists of double-walled hollow metal sphere. So this is your double-walled hollow metal sphere with a small aperture or hole. Now the inner surface of this metal sphere is painted with lamp black. Inner surface of this metal sphere is painted with lamp black. And opposite to this hole, we are placing a conical projection. Why you are using conical projection here means to avoid direct reflection. To avoid direct reflection of radiation, we are placing a conical projection opposite to this hole. Now when light is entering into this hollow metal sphere, it undergoes multiple reflections, and after some time the radiation is absorbed by the lamp black. Now when you heat this black body radiator, it will emit all the radiations through this hole. So whatever the radiation it has absorbed, all the radiations will be emitted through this hole. So this hole or aperture is regarded as our black body. It is regarded as our black body. So next we will see the spectrum of black body radiation. So we have already seen that Lummer and Prinkstream, they have performed a series of experiments and they have plotted a graph between wavelength and energy. Wavelength and energy or intensity. So this graph is showing you the distribution of energy or intensity of radiation among different wavelengths and at various temperatures. So what are the points that we are observing from this graph means? You can see here, first point is energy is not uniformly distributed. First point that we are observing from this graph is energy is not uniformly distributed. At some points you can see energy is maximum, at some points energy is minimum. So energy is not uniformly distributed. Second one, at a particular temperature. At a particular temperature, suppose you consider this 400 Kelvin, this temperature, what is happening as wavelength is increasing. As you are increasing wavelength, what is happening to energy or intensity? It is increasing, becoming maximum and then decreasing. Okay, so that is the second point. At a particular temperature T, as wavelength is increasing, energy increases, becomes maximum and then decreases. And third one is the wavelength corresponding to maximum energy is represented by lambda m. The wavelength corresponding to maximum energy is represented by lambda m. So here this is your lambda m. Why? Because this is a wavelength which is corresponding to maximum energy. This is your maximum energy. So here this is a wavelength, this is your maximum energy. This is a wavelength, this is your maximum energy. So this is lambda m here, this is lambda m. So the wavelength corresponding to maximum energy is represented by lambda m. And as temperature is increasing, as you are increasing the temperature, what is happening to lambda m? It shifts towards a shorter wavelengths. As temperature is increasing, lambda m is shifting towards shorter wavelengths. You can see here what is the wavelength of this red color light? 724. And what is the wavelength at this temperature? 5000 Kelvin? 579. At this temperature, your wavelength lambda m is 483. So as temperature is increasing, what is happening to lambda m? It is decreasing. So as temperature is increasing, lambda m shift towards shorter wavelength. And here you can also observe that at 4000, when the temperature of the black body radiator is 4000 Kelvin, it is emitting which color light? Here you can see red color light. And if the temperature is 5000 Kelvin, it emits green color light. And if the temperature is 6000 Kelvin, it will emit blue color or violet color light here. Okay, so these are the points that we observe from the graph. You can see here the energy, first point is what? The energy is not uniformly distributed in the radiation spectrum of black body. Second one, at a given temperature with increase in wavelength, the intensity of radiation increases, becomes maximum and then decreases. The wavelength corresponding to the maximum energy is represented by lambda m, and lambda m shift towards shorter wavelengths as the temperature increases. These are the references of this topic. Thank you.